Good morning, everybody, and welcome to this event which so many mathematicians have been looking forward to with real great anticipation. Not apprehension, but anticipation. And this is the, let me welcome you all on behalf of the International Center for Theoretical Sciences of the TIFR, which is actually in Bangalore, but we also this is our home institute, so we do some programs over here. And we are especially very happy to have Professor Peter Scholze from the University of Bonn to give the third lecture series of the Srinivasa Ramanujan lecture series. So I will, before I actually hand over the proceedings to other people, I would like to take a few minutes of your time to remind you or even tell you for the first time, in case you have not been here, about what the ICTS does. Okay, so ICTS is a center of the Tata Institute of Fundamental Research. It's a new concept in Indian science of a new type of institute, and it has three basic objectives. And vision is to have programs, in-house research and outreach all combined in one institution. So as far as programs are concerned, of which this is one of them, we provide a platform and resources for researchers to congregate over extended periods of time, encouraging cross-disciplinary immersions and collaborations, and also bringing theory face to face with experiment, because this word theoretical sciences is a little bit misleading. Also, one of the things we do is to incubate new important emerging areas of research and help also create new areas of research. And this is an ambition that someday a new area of research will be created at the ICTS. Also fostering important research areas in which the effort in India needs to be enhanced. This is a very important thing. And this is all brought about by a very carefully conceived set of high quality programs and embedded short conferences which are overseen by an excellent and diverse faculty and visitors. So there's a sort of visitors and adjunct faculty also play a very important role in our center. So this is about one slide on in-house research. So presently the areas we have developed are astrophysical relativity, and this is a math area, dynamical systems and data assimilation, uncertainty quantification, then statistical physics, turbulence, string theory and quantum gravity, and also theoretical biology. So these are the areas which are currently being pursued as in-house research areas in ICTS. Okay, so then there are some other informations about the ICTS, how we are growing. We have a very vibrant postdoctoral program. We have graduate students coming in, and lots of visitors and also visiting students comprise part of this type of activity. So this is the in-house churning that goes on. And then, of course, very important in India is, or in any nation, I think, is to spread the word of science and the scientific ethos, to create the next generation of scientists and mathematicians. And for this, we have an outreach. Outreach is part of the ICTS, so that its facilities can be adapted and used for programs in science education and communication. And basically, let me tell you that I think we had an extremely important outreach program in Bangalore recently. So you may know that last year, 2013, was the Mathematics of Planet Earth year, and the ICTS organized in collaboration with the TIFR Center for Applicable Mathematics and the Srishti School of Technology exhibition on mathematics. And this exhibition actually was at the Visvesvaraya Technological Museum in Bangalore, and about 30 to 35,000 people visited that museum in a matter of about 10 days. And I think this was a very great contribution, I think, of the TIFR to mathematics outreach. This exhibition is traveling in India now, actually in various cities, and it might arrive in Mumbai, depending on your enthusiasm to host it over here. Okay, so our location, the ICTS campus is located over here in North Bangalore, which is the airport over here, and this is the Indian Institute of Science. It's about 30 minutes from here to here. In reasonably good traffic, it's 30 minutes, so we are very near. And we already will always have a footprint in the Indian Institute of Science, even after we move to our new campus, actually. And this is how the campus looks. About 45% is built up. And now it brings me to tell you a little bit about recent programs. So our landscape is very broad. It involves all areas of theoretical sciences, from quantitative biology to condensed matter physics to particle physics, cosmology, string theory, and also very important applied mathematics areas like data assimilation. Okay, so ICTS, besides all the things it does, now it also conducts 3 series of lectures. One is the Chandrasekhar lecture series for the physical sciences, which was the first one and has been extremely successful. So what we do is basically invite one lecturer to give these series, and around him there develops a certain discussion of the area of interest in which these lectures are held. So we have the Chandrasekhar series, the Ramanujan series, and the Alan Turing series. Okay, and today what we have is the Ramanujan lecture series, the third one. The first one was by Professor Peter Sarnak on the generalized Ramanujan conjectures and applications. The second one was on mathematical perspectives on clouds, climate, tropical, and meteorology. So you may notice that in ICTS we don't distinguish between mathematics and applied mathematics and all that type of stuff. I mean, mathematics is mathematics, and mathematics is then applied to very interesting problems in physics, biology, chemistry, everywhere. So that's our attitude towards mathematics. And today we have Professor Peter Scholze talking about locally symmetric spaces and Galois representations. Our next upcoming Ramanujan lecture series is by Professor Chandrasekhar Khare, who is here. That will be towards the end of this year, right? Okay, so now having said all this, I would like to basically invite Professor Raghunathan and Professor Scholze to come here. We'd like to have a memento from the ICTS presented to you. So now, may I invite Dipendra Prasad to introduce the speaker, and then just we have the lecture.
I'm very honored to say a few words of introduction for Peter Scholze, who is giving this series of Ramanujan lectures. Peter Scholze was born in 1987 in Dresden, East Germany. He obtained his PhD in 2012 under the supervision of Michael Rappaport at the University of Bonn. And immediately after PhD, for his many works before PhD and for his PhD work, he was made a full professor at the University of Bonn at the age of 24, which is the youngest, which makes him the youngest professor in Germany. His initial works were on the cohomology of Shimura varieties and the Langlands program. And later on in his PhD thesis, he developed a theory of perfectoid spaces, which gives a method to compare objects in characteristic P to objects in characteristic 0, and has made various applications of this theory, which has become one of the most important developments in mathematics for many years. Recently at MSRI, there was a full-scale conference on his work, Hot Topics Conference in February 2014. And just before that, he gave Master and Morse lectures at the Institute for Advanced Study on his works. So at the very young age of 26, he is one of the most accomplished mathematicians. Before I gave him the stage, Chandan Dalawat showed me that he has been already a very well-known figure from 2005. His name seems to have appeared in Berlin newspapers when he won maybe the 4th time the Olympiad gold medal. So he got 1 silver and 3 golds, and there is an article which Dalawat printed out for me, and I will just read out something from there. So it says that already from the 7th grade, the young boy has been taking part in the Olympiad programs. Even in the metros, the 17-year-old thinks about calculations and solutions to problems. In fact, when I went to meet him yesterday at President, he was doing the same. All right, so with these few words, I invite him on behalf of ICTS to give these lectures.
Well, thanks a lot for the introduction, and many thanks for the invitation to come to India. So it's my 2nd trip under Ramanujan's name in some sense. Yeah, I'm very glad to be here and to give these lectures. So I want to talk some works that I did on locally symmetric spaces and their homology. But in this first lecture, I just want to try to be as basic as possible. So something that's very important for some of these talks is Galois theory. So let me first give the title of the lecture. Symmetric spaces. And so I need to recall a bit about what Galois theory is about. So Galois theory is somehow about, it's a fundamental importance number theory. So number theory, what you consider are the rational numbers and somehow algebraic equations over the rational numbers. In particular, you are interested in those complex numbers which are a solution to some algebraic equation over the rational numbers. So those are called the algebraic numbers. So you have the complex numbers, and there you have the algebraic numbers, which are those complex numbers for which there exists some polynomial p of x, so x to the n plus some coefficients, which are rational numbers, such that x, the small x, is a solution to this. And in fact, I decided to rename this as alpha to avoid any conflict of notation. So those are the algebraic numbers. And some of the basic point of Galois theory is that there is no algebraic way of distinguishing say the square root of 2 from minus the square root of 2. So both are solutions to this equation that x squared minus 2 is equal to 0. And if you think in terms of real numbers, then you will say that this is a positive root and this is a negative root, but that's somehow not an algebraic way. So you're just allowed to make conditions which are algebraic equations, such as And well, both of them satisfy this algebraic equation, but there's no other algebraic equation that they satisfy. So one way to make this idea precise is to look at what's called the Galois group, so the absolute Galois group. The Galois group of Q bar over Q, which is just the group of automorphisms of this field Q bar. So that's a set of bijections which commute with addition and multiplication. Maybe I use C as a blackboard. And so whenever I have an algebraic number, so there is some polynomial which kills it. And so in particular, this implies that if I look at the orbit of this Galois group on alpha, then this will be a finite set. Namely, whenever I have such an automorphism, because it commutes with addition and multiplication, it will also commute with any polynomial with rational coefficients. So this will be gamma times p of alpha. But this is 0. So that's still 0. And so that's contained in the set of all x such that p of x is 0. And so that's a finite set. And so you can make this Galois group into a topological group. By asking that, how do I want to formulate this? That for all algebraic numbers in Q bar, the map which sends gamma applied to alpha is a continuous map. So that's equivalent to asking that for all, because this is a finite set in particular, the preimage of alpha itself is an open subgroup. So this means that for all alpha in Q bar is a stabilizer of alpha. Is an open subgroup. And so in this way, this becomes a topological group, but it's not the usual kind of topological group. So it's not like n by n real matrices or so, simply because it has lots of open subgroups, which is not the case usually. So this makes this absolute Galois group totally disconnected, so it's some kind of Cantor set. Totally disconnected. Okay. And so up to now I was mostly considering all algebraic numbers, but it's better somehow to exhaust it by all finite extensions of Q. So, and there are some particular ones that are important. So, finite extension K over Q, say contained in Q bar. Is Galois if it is stable under the Galois group action. And then one can also define a Galois group of this finite extension. So the automorphisms just of this finite extension. And so at this point, let me give some examples for what happens here. So one thing you might take is a field K, which is Q, to which you join a square root of 2, or in other words, a set of A times plus B times the square root of 2, where A and B are rational numbers. From the field. And this is Galois, because if you apply the absolute Galois group to the square root of 2, then as I indicated earlier, this gives you all the possible solutions to this minimal polynomial that it satisfies. So square root of 2 and minus square root of 2. And both of these are already contained in this field. And so in particular, the whole field is stable under this action. And if I look at just the Galois group of this extension, then that's isomorphic to the symmetric group on 2 elements, where this set with 2 elements is just the set of square root of 2 and minus square root of 2. So in other words, there are 2 automorphisms of this guy. One is just the identity, and the other is a map which sends A plus B times square root of 2 to A minus B times square root of 2. Then you might look at bigger extensions. So you might take a join a third square root of 2. In this case, third square root of 4, say A, B, C, and Q. Again, that's a field. So this is not Galois this time. So the third square root of 2 is of course a solution to x squared minus 2 equal to 0. And if you look at all solutions, then this would be, well, this square root. But then you can also multiply this by roots of unity, the third roots of unity. So if you look at this in the complex plane, then I don't know, would look. So somewhere here you have 2, somewhere here you would have 1, then you have the third square root of 2 somewhere here. But then you have 2 other points here and there. E to the 2 pi. Such that if you take the third power, this again lands on the real line and gives 2. So in particular, it's not Galois because these are not all contained in this field. Namely, this field is manifestly contained in the real numbers, but these other 2 roots, they are not real. So that's one way to see this. But what you can do then is you can look at the field you get by also adjoining this third root of unity to the picture. And then this will be Galois. And the Galois group will now be the symmetric group on 3 elements, while the action on this 3 element set. All right. And so the basic theorem of Galois theory is that you can classify finite extensions of Q bar, so by open subgroups. Of this absolute Galois group. So how does this correspondence go? In one direction, it takes a field and sends it to the set of all such gamma, such that for all elements in the field, gamma fixes this element. So it's a pointwise stabilizer of this field. And in the other direction, if you have a group H, you send it to all those algebraic elements which are fixed under H, so meaning all those alpha, such that for all gamma in H, gamma times alpha is equal to alpha. And then there are also enough of these Galois extensions. So under this correspondence, a finite extension is Galois if and only if H is normal, in which case the Galois group of K over Q will just be the quotient of the absolute Galois group of Q by the subgroup H. And you can also exhaust all of Q bar by the union of all finite Galois extensions. And this makes the absolute Galois group of Q bar the inverse limit of all the Galois groups of these finite extensions. So those are just finite groups. And so this shows that this absolute Galois group is a profinite group. Profinite just meaning it's an inverse limit of finite ones. And so in other words, when you study this absolute Galois group of Q, that's just a different way of saying that you study all these individual Galois groups of all these finite extensions. And so I gave you some examples there. And somehow very interesting business to understand what can happen here. For example, it's an open problem whether any finite group can appear as such a Galois group here. And so one way one can try to understand this absolute Galois group is via maps to some kind of general class of groups that come up. So it's maps to finite groups of Lie type. So something like GLN of a finite field FP. So if you look at the classification of finite simple groups, and almost all of them are some finite groups of Lie type. So that's a pretty general setup here. So this is supposed to motivate the following definition. So the finite Galois representation is a continuous map rho from this absolute Galois group to some GLN FP. I mean, later on I might also allow bigger extensions of FP here, but never mind for the moment. So sometimes I also call this a mod P Galois representation. So let me note that in this case, the kernel H, which is the kernel of rho, is an open normal subgroup. So you can look at the field one might call K of rho, which is some of this fixed field of Q bar under the subgroup H, is a finite normal extension of Q, and so this representation will factor over the absolute Galois, over the Galois group of this guy. So you get rho, which is a map from, and embeds it into GLN. So a different way of thinking about such a mod P Galois representation is that what you have to do is you have to give yourself some finite extension of the rational numbers whose Galois group is of a special form that it somehow sits inside GLN of P, and somehow generically you should think of it as being really equal to GLN of P. So you're really considering such finite extensions of the rational numbers which have this very fixed symmetry group. And it's not so clear how to produce them explicitly. So I don't have to erase, I realize. Okay, so, but those objects come about in nature, actually. So that's the basic diagram that these talks are about. So, so in the middle you have such finite Galois representations. And then on the one hand, you can look at what are called varieties over Q, algebraic varieties. So these are just, essentially by definition, just systems of polynomial equations. Where all the polynomials have coefficients in the rational numbers. I will give an example for this in a second. So, and then there's a procedure called rhetorical homology, which takes any such variety and produces for you a finite Galois representation. And this procedure captures a surprising lot of information about the system of polynomial equations. So there's some kind of motivic philosophy that somehow, in some sense, everything about the variety should be inside these finite Galois representations. And on the other hand, these finite Galois representations are linked in a much more mysterious way to what the topic of this lecture series is. So the torsion in the cohomology, or homology, to make it a bit simpler, of locally symmetric spaces. And somehow there are even two ways now. So it's called A and B. So there are two important conjectures. Conjecture A here would say that torsion in this cohomology of locally symmetric spaces gives rise to Galois representations. And conjecture B, which is usually called Serre's conjecture, says that, well, not quite all, but up to some very minor almost, all finite Galois representations appear in this way. And so this lecture series is just about problem A, and then there is this other problem B, which I will not say nothing about. So this lecture series. Is about A. And so before really going into this, I want to explain a very famous example of why this is useful. So so let's consider E over Q some elliptic curve. So that's now an object which belongs to this side. So what is an elliptic curve? So an elliptic curve has a zero section. And if you remove the zero section from E, then this is given by a very simple equation. So some kind of cubic equation, two variables, which you can bring into this form. X squared, y squared is equal to x cubed plus ax plus b. Where a and b are certain rational numbers, pick any, such that the determinant, which is 4a cubed plus 27b squared, is not 0. Yes. So if you look at the real points of this elliptic curve, so at all pairs of real numbers x and y which satisfy this equation, then the typical picture is that you have some blob here and then something which goes off to infinity here. And then somewhere this meets infinity, and that's the point 0. And in this picture, one can explain that for, in fact, any characteristic 0 field, K, if you look at the K-valued points of E, that this is an abelian group. With zero section 0. And that's why it's called 0, although it's somewhere at infinity. So how does this work? So you intersect this, this cubic equation with a line which gives you 3 intersection points P, Q, and R. And what you ask is that whenever you do this, the sum P plus Q plus R will be equal to 0. And it's a non-trivial theorem to check that this actually defines the structure of an abelian group on this guy. And you can also look at the complex points, in which case what you get will be a complex torus. Or, writing it differently, it's a quotient of the complex numbers by a lattice lambda. So lambda isomorphic to Z2 inside of C is a lattice. So here somewhere this lattice, and then this continues periodically. And what you do is you identify opposite sides. So you glue this side, glue these sides together and these sides together, and then you see that you get such a torus. Okay, and so how do we get from this picture to such finite Galois representations? So what we do is the following. So we look at the n torsion points, so fix some integer n greater or equal to 1. So that's the kernel multiplication by n on the elliptic curve. Then you can look at, if you do this over the complex numbers, then you see, so if say n is 3, then the 3 torsion points will just be those 9 points here, which is somehow this lattice scaled back by n. So this is just 1 over n times lambda mod lambda, which is just, because lambda is just z squared, so it's just z mod n squared. So with the complex numbers, there are precisely n squared torsion points. But because everything in this elliptic curve is defined by algebraic equations, all of these complex numbers have in fact to be algebraic numbers. So this in fact has to be equal to E of Q bar. But now you have the absolute Galois group of Q acting on Q bar, so you get an action of the absolute Galois group of Q bar on these n torsion points. And now we can take for this n, say, a prime number. And then we get a Galois representation attached to, Galois representation rho attached to this elliptic curve E and this prime number P, which goes from the absolute Galois group of Q to the automorphisms of this P torsion, which is just GO2FP. I mean, this P torsion is just FP squared, and then the automorphisms are GL2FP. Okay, and so this is just a very special case of this very general construction of Grothendieck of étale homology. Okay, and so what is this good for? So now let's take a prime number P at least 5, and let's look at a solution to the equation A to the P plus B to the P is equal to C to the P. So where A, B, C, say, are positive integers. And of course, we want to show that this is impossible. So in order to prove Fermat's last theorem. And then it was Frey suggested to look at the following curve, the following elliptic curve, which is given by the equation. It's in the form slightly different from what I wrote there, but it doesn't matter. So any cubic equation will be good. X minus x times x minus a to the p times x plus b to the p. So in this case, if you look at the differences of the zeros here, so x equal to 0 is the solution to this, and x equal to a to the p, so their difference is a to the p. and the difference here will be b to the p. And the difference between those two solutions is a to the p plus b to the p, but by our assumption, that's again a p's power, and that's somehow where. So in particular, this implies that delta is just abc to the 2p. It's a p's power. And this property that delta is a p's power is somewhat critical to what will happen in a second. So we get this finite Galois representation attached to this elliptic curve, and we take the same p as we chose here. So it goes from the absolute Galois group of Q to GL2FP. And then there is something funny about the geometry of this elliptic curve. And this implies the following fact. I will not exactly explain what this means, but this representation is unramified outside the primes 2 and p. And there's also very little ramification at those two primes. So you should think of these properties as properties of this extension K of rho that you wrote down. So this extension K of rho is an extension of Q with Galois group GL2FP. Which is unramified outside only two, which is ramified at only two primes, and also at those two primes there's very little ramification. And then there is the feeling that such things shouldn't really exist. And this feeling is made precise by the conjecture of Serre. Which in this case says that this Galois representation should come from some torsion in some homology of some locally symmetric space, but you can make this completely explicit here. So it comes from in this case, it will be a modular form of weight 2 and some level which is some very small level at 2. We'll explain in a second more precisely what this means, but the point is that there are no such forms. You can just explicitly compute all modular forms of some given weight and some given level. And in this case, you just see there are no such guys. And so this means that some of these elliptic curves that we are contemplating here cannot really exist. So this means that solutions can't really exist. And hence, Fermat's last theorem is true. And this conjecture of Serre was proved in full generality by Carré and Vinton-Berger. But the specific case that was needed for Fermat's last theorem is this very famous work of Wiles, finished by Taylor and Wiles. Which really got this whole business started. So the upshot of this is that some algebraic varieties of a Q, that's something we're really interested in. That just amounts to solving polynomial equations of the rational numbers in some sense. And so by some very general procedure, we can pass these finite Galois representations. And from knowing the geometry, we can deduce very special properties of these Galois representations. But on the other hand, there's this other completely disparate picture here of these locally symmetric spaces. And if Sayre's conjecture is always true, then somehow we can always look up whether this is really possible that such a Galois representation exists by just computing this torsion, this homology of this locally symmetric space. And if there is nothing there, then somehow what we are contemplating can't really exist. Okay. So another remark I want to make is that over arbitrary finite extensions of Q. So for example, in this, so in this example, I only considered elliptic curves over Q, but really it should be okay to consider elliptic curves over any number field. So you should have algebraic varieties over any K on the left-hand side. And again, you can use Hitachi homology to pass to finite Galois representations. Some are off the absolute Galois group now of Q bar over K. And again, you have torsion, blah, blah, blah here, and some of both of these should be okay. And maybe I should also say that so the conjunction of A and B is some kind of mod P global lengthness correspondence. So in the usual global lengthness correspondence, what you compare are, on the one hand, some kind of not finite Galois representations, but Galois representations into characteristic zero fields. And on the other hand, you have some kind of automorphic forms. And these automorphic forms are just certain forms on locally symmetric spaces obeying some high, which encodes a high symmetry. And if you think about it, that's some kind of mod P version of this global lengthness correspondence. And so this in this global lengthness correspondence, you have two problems. On the one hand, you have to attach Galois representations to automorphic forms, which is this part A. And on the other hand, you have to show that all Galois representations really come from automorphic forms, which is this part B. Okay, and so in this lecture series, I want to consider two specific examples. So up to now, I was mostly considering a general N and a general number field and so on. But let's consider two specific cases. So the most classical one is the one where N is 2 and K is the rational numbers, which is also the case that some of this original conjecture of Sayre is about. And then I will also stick to the case that N is 2, but I will consider a field which is just a bit larger than Q. So it's, you take Q and you join the square root of -1. So I. So this one. So that's an imaginary quadratic field. And really what I will say about this example pertains to any imaginary quadratic field, but for concreteness, I will stick to this one. And so today I will just recall the classical theory, which happens in this case A, but I want to say that even if you're only interested in the rational numbers, as soon as you leave the case n equal to 2 and go to bigger n, some of the situation will be very similar to what happens in this case B. So n greater than 2, k equal to q, very similar to B. And in fact, somehow, this case A is really a very special case, and in almost all cases you will see the phenomena that I will mention in case B. It's just that the case B is somehow the case of lowest dimension where this happens. So that's why I stick to this one. But okay, today I will just recall what happens in this case of the rational numbers, so for GL2 over the rational numbers. So that's the business of modular curves. So first of all, you have this symmetric space, which is a two-dimensional hyperbolic space. So one way to look at this is that it's a set of complex numbers, let's call it tau, whose imaginary part is positive. So that's just the real numbers cross the positive real numbers. So xy maps to x plus iy. And you have a metric on it. So hope I got this right. Y squared. So that's two-dimensional hyperbolic space. And it has its group of isometries, and this group is just PSL2 of R. So if you take some ABCD, say, in there, then this will act by mapping tau to A tau plus B over C tau plus D. And then I take some gamma contained in SL2 of the integers, some so-called congruence subgroup. So this means that gamma contains all those gamma which are congruent to one modulus some big integer n, which is sometimes also called gamma of n. So it's just this congruence subgroup which is given by some congruence condition on the entries of this matrix. And in fact, I will assume slightly stronger that gamma actually contains a subgroup of the form gamma 1 of n for a technical reason, which are those gammas which are congruent to some such matrix. It's not very important, but to make one statement true later on, I need this. And it doesn't really, it's almost as general as a general case. And then one defines a modular curve as this locally symmetric variety, or locally symmetric space. Which is the complex upper half plane divided by this subgroup gamma. So for example, if gamma is the full SL2Z, one can draw a picture of this, which is this, again, famous picture. So you have somewhere your complex upper half plane here, so you have somewhere 0, somewhere you have 1, somewhere you have I, somewhere you have -1 maybe. Then you draw these straight lines going up from the integers. And then you also draw some circles. So here's 1 plus I, here's -1 plus I. And then the region above those two circles here and between those two lines, that's a fundamental domain for this quotient of H2 mod gamma. So you get this actual quotient if you identify these opposite sides here, and you also identify these two guys here. So in this picture, there's something funny going on at these points here, which are so-called orbifold points. But if I make my group a bit smaller, so if gamma is sufficiently small, then this H2 mod gamma will be a real manifold. In fact, a hyperbolic one. But then, in fact, it's a complex manifold. And as a complex manifold, it's just a one-dimensional complex. So this also explains the name modular curve. So this curve refers to it being one-dimensional with complex numbers. But then there is this famous theorem that, in fact, H2 mod gamma carries a unique structure as an algebraic curve. Over the complex numbers, but in fact, and here I'm using a bit that my assumption on gamma containing gamma 1 of n, is already defined over the rational numbers. So this means that this H2 mod gamma is just a complex points, complex solutions to some system of algebraic equations over the rational numbers. In fact, if gamma is some small subgroup, you can really just explicitly write down the equations defining this guy. So this means that this guy, which a priori started life just as some kind of topological or as some kind of real manifold, somehow got more and more structure, and eventually somehow it's just something really algebraic. It's some system of algebraic equations over the rational numbers. And I said that in this business, we are always interested in the homology of these guys. And so if I look at the homology of this guy with integer coefficients, then this is torsion free. For I 0 and 1, and it's trivial otherwise. Something rather simple. And so somehow, in some sense, it's given by its rank, and to compute the rank, I can do it over the complex numbers. And so there I can use Hodge theory. And Hodge theory tells us that, well, somehow the H0 is not interesting anyway, it's just Z. So H0 is just Z, it's boring. So somehow what we're interested in is the H1 of this guy. So that's just the extension of this guy. This can be computed in terms of in terms of harmonic functions in general. And here these harmonic functions that appear have the name of way 2 modular forms. Of level this chosen congruent subgroup gamma. So those are functions from H2 to C such that they obey a symmetry under this. So if I have A, B, C, D in my congruent subgroup gamma, then they should satisfy some equation of this form. And I'm never sure whether to put plus or minus here. I apologize. Because sometimes this is brought to the other side. But the 2 here is some of the weight. So on the other hand, as H2 mod gamma is an algebraic variety over Q, you know that if you look at somehow, this is what I call torsion homology. So you consider the homology with some torsion coefficients Fp. This guy will carry an action of the absolute Galois group. And this, again, this business is called Etoile homology. That implies this. So you have an action of the absolute Galois group of Q on this guy, which is just the reduction of this first homology group with integer coefficients to Fp. So the picture here is the following. So you have this homology of this modular curve, and over the complex numbers, that's given by modular forms of weight 2. And on the other hand, if you use it mod P, you get to Galois representations. And that's how this link A here comes about. So this gives A in this case. So in this case, the torsion homology, this group here, really has an honest Galois action on it. And that's how you go from some of these torsion element there to Galois representations in this case. And so, in particular, one way to make Serre's conjecture, to make a precise statement of Serre's conjecture is the following. So Serre's conjecture is equivalent to this representation we are considering there. Appears as a subquotient for the action of the absolute Galois group on that guy we were considering. And yeah, that's what I wanted to say today. Yes.
So, real torsion classes in homology still make it twice the
And when you go from algebraic varieties to finite Galois representation, you're taking the example homology and choosing a lattice, QT coefficients.
Well, I'm just taking HI of my algebraic variety